Hello? Hello? How much? Yeah. Can you hear me? Great. Okay, perfect. So, hello everyone. Welcome to Small Molecule Identification with SIRIUS. First of all, if you have not yet downloaded the workshop data and want to participate in the live demo part, then you can still now download it in case there's internet connection. Do you have internet connection here? Yes, it's working? Okay, perfect. Because otherwise, if somebody has problems, you also have a few USB sticks with the data on it. So then just like raise your hand and Fleming will bring you the stick. Okay, so, okay, now everybody else is joining. Then I wait a few seconds before we start. Okay, great, pretty full. Then let's start. So I will start with a brief introduction about the background and what all the tools do. And at first I want to give you a short overview what SIRIUS is meant for. So what kind of data do you need to use SIRIUS? And it's all about identifying small molecules, so molecules that have less than 200 atoms or less than 1,000 Dalton. You need high-res data. We only annotate single-charged features, and ideally you would have an MS1 isotope pattern, and also, that's the most important part, an information-rich fragment spectrum. Given the right data, SIRIUS basically gives you a comprehensive small molecule annotation workflow that allows you to identify suspects, so molecules with reference standards and spectral libraries. But more importantly, it also allows you to annotate unknown molecules, so molecules that are cataloged in structured databases. Further, we have also methods in there that allow you to find novel molecules, so true unknown unknowns that were previously undiscovered and not yet elucidated. All of this is packed into a quite complex workflow. Unfortunately, it's much easier in the software. And I will now try to walk you through this workflow a bit so that you know what all the bits and pieces mean and what they are good for. First of all, I want to start with preprocessing and the data import. And in general, as soon as you are getting started in SIRIUS, data is already preprocessed. So we are working already on the aligned features usually. So what does the preprocessing do? You might know that, can you see my mouse? Not really, okay. Wait, I have to check where I can get the cursor. Here. This is working, okay, perfect. So as you know, your LC-MS data is three-dimensional data, so you have your over retention time from your chromatography. You're separating your compounds, and the mass spec is then measuring MS1 and MS spectra of these compounds, and the job of the preprocessing is basically to detect these features, to assign possible adducts, detect isotopes and grouping them, and if you have multiple runs, to align the features so that you know which feature belongs to which over multiple runs. For SIRIUS, the important part is that we basically, for a feature, extract the isotope pattern here in green and red, and we need a feature-rich fragment spectrum. So the interesting thing here is basically that SIRIUS really loves it if you have many fragments peaks. So in case you can measure multiple collision energies, it's always good to give them all, or merging ramped spectra or whatever, merged spectra, everything fine. It doesn't matter whether they are separated or not. The important thing is that we have the fragments. And another important thing is basically obviously the precursor mass that needs to be known, but this is given in LC-MS. And also important are the neutral losses, but I can come back to that later. So there are two ways to get your data into SIRIUS. Either you already have your data in some open format, so usually MZML, and then you can do the preprocessing directly in SIRIUS. So SIRIUS does not support any vendor formats, just open formats. But if you have these open formats, you can do the preprocessing in SIRIUS. And this is like a fully automated preprocessing, so you cannot and must not, you cannot and also don't have to interact with it. It has no parameters, no settings, but it works for DDA data only. And yeah, then you get basically like everything directly into SIRIUS. And the other option is basically that you are using a more preprocessing focused tool. So SIRIUS is really focused on compound annotation, like MZMine or MSDial or Edgenet Mars Hunter. And if you're using one of these tools, you basically can export peak list formats that are all supported by SIRIUS. So MZMine, for example, has a specific SIRIUS export function. The good thing here is they support vendor formats. You get more visualization and it's more interactive, but it also means you have to interact with it. And you have like to set parameters and know a bit more about the preprocessing. So in general, both is fine. Yeah, so all the tools I showed can do all the necessary things we need for preprocessing. And my suggestion is basically, if you want to have like more control over the preprocessing, use MZMine and SIRIUS. And if you want like a fully automated preprocessing, then just give the included preprocessing in SIRIUS a try. Just like as a side note, all file formats supported by SIRIUS are plain text files. So in case you are wondering that like something looks strange after import, it's always worth to open it in a text editor and look if there's something useful in there, or if it's maybe empty or some gibberish is in the files. So this is how an MSNovelist file, for example, looks like, and this is like how our SIRIUS MS peak list format looks like. So I think that's it about like getting data into it and about what kind of data you need. Now I want to like emphasize the core concept of SIRIUS, and I think the most important thing to understand is that SIRIUS is basically able to compare spectra against structure. And this is a very flexible and powerful approach, and it does that by using a so-called molecular fingerprint. And the interesting thing is, with this approach, you can basically have structures from any various sources. So if you can draw the structure, if you can like have it in a structure database, if you have it in a spectral library, if you compute some transformation products, you can all throw it into. What is the molecular fingerprint? The molecular fingerprint is basically a long list of molecular properties. The easiest thing to think about it is that it is a long list of like some kind of substructures. In reality, it can also be paths or just elements, but in general, it's a long list of substructures. And if you have a molecule, it's very easy to produce such a fingerprint. You just like look into the molecule, is this property there? And if yes, you write a 1, and if no, you write a 0. And this gives you the molecular fingerprint, so like a structural representation of your molecule. The more complex step is basically how can you get from a spectrum to such a molecular fingerprint. And this is basically what CSI FingerID is doing. So if we now go back to our workflow here, we see here is like the tool CSI FingerID, and we have to compute molecular formulas first to like use CSI FingerID to predict a molecular fingerprint, which is the thing we need to search against structures. So let's focus on how we get the molecular formulas in SIRIUS. We use two kinds of information for that. One is the isotope pattern from the MS1. I will just like shortly explain that. The idea is basically that for any molecular formula given, I will talk about that later, we can basically simulate a theoretical isotope pattern and can compare it against the measured one. And this comparison gives us a score, and based on the score, we can rank molecular formula candidates, rank molecular formula candidates to see how well they fit the measured isotope pattern. And the second, usually more important part is that we use the fragmentation spectrum to compute fragmentation trees. And these allow also like to get a score about how well such a tree explains the fragmentation spectrum. How does that work? So the basic idea is that we know the precursor mass and we have our fragment spectrum here, and we have a list of molecular formula candidates. Where this candidate list comes from, I will explain later, but for now just assume there are candidates. And what we do basically is for each of these candidate molecular formulas, we compute, so like a candidate formula means it has the mass of the precursor, right? We compute a so-called fragmentation tree. So there are many fragmentation trees possible. For each candidate, we solve an optimization problem to find the tree that explains the spectrum best, and such a tree has a score. So the root of the tree is always the precursor formula candidate, and then for each fragment, we also like find the best matching fragment formula, and the edges in the tree basically representing neutral losses. And based on how well does the formula fit the fragment mass and how common is the loss that's needed to produce this fragment, we also get a score. And we then have to do this for all candidates, and based on that, we can basically, in combination with the isotope pattern score and the tree score, compute what's in the software called SIRIUS score, and that's giving you a ranking of your formula candidates. Like this. Yeah, so now is the question, where do the candidates come from? And this is like quite new. This is there since SIRIUS 6, that there are like 3 different formula generation strategies, so we simplified this step a lot. And these 3, the first basically is the novo formula annotation. So what we do for the novo formula annotation is basically that you have your precursor mass plus some mass deviation, and then we generate really all possible molecular formula given a specific set of elements. So for this mass, like 614, we basically generate, given CHNOPS as elements, this would be like 1,219 molecular formula candidates. And if we now add a few more elements, we already see, okay, that grows rapidly. So we now would get like over 14,000 of such candidates. So that can be quite computational intense. That's also why it's not a good idea to just like enable all elements you know and start a computation. It's, yeah, and like to help you a bit with this, in SIRIUS you also have like some auto-detection functionality that tries like to detect which elements are likely present in a given MSM spectrum. Yeah, so usually like you just like take the auto detection, but obviously there are a few elements that are very hard to detect, which are usually the elements that do not have a very like significant isotope pattern. Yeah, and like what's the good thing about generating all possible formulas and ranking them? The good thing is you can find truly novel structures with it, because you can find truly novel formulas. And the bad thing is it's slow, and you need to somehow define the set of elements allowed. So then there is a second formula generation strategy, which is database search. Database search basically says, okay, let's look into a structure database of your choice. It can be PubChem, it can be like the set of all biological database SIRIUS comes with, and just look up which formulas fit the mass plus deviation. Like for PubChem, for our example, this would be 191 candidates, and for like the combined biodatabase, it would be just 3. So this is extremely fast. You don't have to care about elements because they are given by the database. But the problem is you will never find a novel formula. So as soon you are dealing with a true novel candidate, this will not help you. And there is some like in-between strategy. First, this was like presented by Singh et al. In MS-Buddy, which is a bottom-up formula search. What's the idea behind that? the idea is that we also take database formulas and then try to transform them into some kind of novel formulas given the fragments and the neutral loss masses from our MS spectrum. So we basically try to generate novel formulas that somehow fit what we have seen in the mass spectrum. The idea is basically you look into the database, get all your precursor formulas, and then you look basically also all the fragment masses in your database and also get all these. And then you also look up all the neutral loss masses in your database and also get them. And then you basically take each of the fragments and add and combine them, each of the fragment formulas, and combine them with each of the loss formulas. And this gives us, for our example, 268 candidates, and some of them are novel formulas, but most of them are database formulas. So this basically like tries to somehow combine being fast and at least giving you some novel formulas. So this is also fast. You don't have to care about elements, and you get at least some novel molecular formulas. And the downside basically is that some molecular formulas might not be covered. So let's wrap this up. It's basically like that. Database search is crazy fast, and it might be a good choice in the case where you are just interested in searching a structured database anyways, right? So if you just do structured database search, it doesn't help you much by having novel formulas because you cannot find a structure for it. So if this is the case, this might be a good strategy. Same holds for the bottom-up search. And then you have like the de novo molecular formula search, which is basically ideal if you want to annotate novels. So then you cannot circumvent this computational effort, basically. What we use in the software by default is basically a combination from de novo and bottom-up. So we basically, like for lower masses where de novo is fast enough, we do it de novo, and we also then do bottom-up search additionally. So you will basically get de novo formulas for your given element set, and additionally also bottom-up formulas from with elements that are not in the element set. But yeah, I think the take-home message here is the default is that we combine de novo with bottom-up, and then you have basically like the choice between these strategies or the combined strategy. So we basically now have our input we need to predict a molecular fingerprint. And what we are interested now is basically comparing it against fingerprints from structures. Where do they come from? So SIRIUS comes with more than 20 built-in structure database. For example, PubChem, but also like databases like HMDB, Norman, FooDB, Lotus, and many more. So these are like built in, they are on our servers, and if you do the search, you will request basically the candidates, score them in your computer, and see the results. So you don't have to do anything here, no database import, no nothing, just starting. And another thing you can do is basically bring your own structures. All you need for that is smiles. So since we can compare against structures, you just have to bring us structures. And if you like import them, what SIRIUS does is it computes molecular fingerprints for all of them, because this is the thing we need to search against the structures. And optionally, you can also bring your reference spectra. So in case you have references that you are particularly interested in or whatever, you can just also throw them in, and everything will be one big database you can search on, and SIRIUS will basically take care of using the spectra or just using the structure, depending on which information is available. And what SIRIUS also does is, for all structures in the database that have a reference spectrum, it computes the fragmentation trees, because we can use them later to generate very nice explanations of your spectrum, because based on this fragmentation tree, we can then basically build, using combinatorial fragmentation, an annotated mass spectrum that like helps you to interpret the result. but Fleming will show that later. Yeah, so take home message here. Every database, every custom database in SIRIUS is just a structured database, and if you have reference spectra, you can just also provide them to get basically also the information which of your candidates have reference hits. And like generating your own structured databases gives you a lot of options. The easiest, most straightforward thing is just, okay, I have a few structures and I want to import them. Next step is I have structures and references, and I want to see which data in my data set also matches my references. The next step you can do is, okay, I have some drugs I'm interested in, and I also want to search against unknown transformation products. That's actually built in since the last version, so we built in biotransformer from David Wishard's group. So in case you import structures into SIRIUS, you can basically say, okay, also compute biotransformations for me. And then you will basically get a database containing your lead structures and possible transformation products. And the good thing is, usually these transformation tools produce also transformation products that might not be true, right? That might not exist. But the cool thing is, since we can compare our spectrum against the structures, it doesn't matter whether there are some structures that does not match anything. It doesn't hurt. So that's pretty powerful. Another thing we have done in 2022 is you can combinatorially, so that's not built in, that's just something you can do, is you can combinatorially generate structures. So for example, we did it basically for bile acid conjugates. So if you know some building blocks, some rules, how structures are built, you can basically apply these rules using some tools that are doing that. There are quite a few out there. And then you can import the resulting structures as a custom database, and then we can search against it. And obviously, what's also possible in case there are generative models that can generate structures, you can also import that data. So, but now we talked a lot about matching against structures, but I also mentioned, okay, spectral libraries are involved. What are they doing? I will make it short. What we're basically doing is SIRIUS ensures that every structure that also has a high library match will be contained in your result list and will be ranked and scored. So you will never miss in your result an annotation that you would have found with library search. So they will always in there, and you will see, okay, library hit here. So basically that means we ensure the structured database is always a superset of the reference libraries. And the other things we are using them for is basically, so I will not talk about Zodiac today, it's basically a network approach to improve formula rankings, and this network will basically also use the identity and the analog library hits as anchors during the algorithm. If you want to hear a bit more about that, I will talk about that in my talk on Wednesday. And I think also quite interesting part is that we use especially the analog hits for visualizations. So Fleming will show you later, we can use the analog spectral library hits to explain your structured database hit. Because the problem usually is if you have such an in silico method, especially if it's based on machine learning, you get some list, something is on top one, and you don't know why. And but if you have an analog hit, it's obviously not a true structure, but if you have a structure hit and an analog hit, and the reference spectrum and the method spectrum, you can again try to connect your structured database hit back to references. But Fleming will show that later. So what does that mean? In the end, you get one single ranked list with your candidates. If there is a reference spectra hit, you can see it here, you see the cosine, and you can click on show more. Here you basically see all the structured databases where this hit is a part of. Yeah, then I briefly started talking about evaluations. Basically, the most of the UI in SIRIUS is about trying to explain the results, because computing is quite easy. You just set a few parameters, click on compute, take a coffee until it's computed, and then you have results to investigate. One thing we do here is basically you can look into the substructure highlighting. We will do this in the live session as well. So you can basically like see our predicted fingerprint, how well does it explain the structure candidate. And if there the other thing we do is we annotate your MSM spectrum with probable fragments of your structure candidate. So you can basically check whether the a fragment of your candidate structure makes sense compared to the peak it was assigned to. The other thing is we have the library matching in there now, so you can link things back to spectra. And the probably most important and most convenient thing is we have a confidence score. So this takes into account a lot of different like metrics, like fragmentation trees, how well do they fit, compound classes, are they like corresponding to the structure, and a lot of more stuff. And this basically gives you, for a ranked list, a value between 0 and 1 that says how sure is the method that the top ranked structure is correct. So this is basically what to look at if you want to know is this a good or a bad annotation. You can even sort by that, filter by that, and focus on the things where you have good, high quality annotations. We have two different kinds of confidence scores, just like to make it a bit more confusing. No, it's because they have different, different use cases. So the basic confidence score is like for an exact hit. So you basically, it says, how sure am I that the top structure is correct? But it sometimes happens that you have like the top 3 structures and they are extremely similar. Like just some functional group has shifted one position, and usually it's pretty hard, sometimes even not possible, like to tell with mass spec whether it's this or this structure. And like to cover these cases as well, because like if your question is the top 1 correct, and second and third look the same, the correct answer is I'm not sure, I don't know. And then you get a low confidence. And then we have the approximate confidence score, which basically highlights you all 3 of the candidates and says they are so similar, I don't know, one of these 3. And yeah, so you can just like, both confidence scores will be computed, and you can just like switch between them in the view. Yeah, so now we talked a lot about comparing against structures that are stored somewhere, but we also like have a method to help you out in cases. So we developed that together with Nicola Zamboni. And this is like MSNovelist, which is a generative model that basically, given the fingerprint again, can generate you novel structures. So they must not be novel, right? So it will also generate structures that are in the database, because if this is the correct structure, it makes sense to generate it. And this will basically give you the possibility to like live, during searching, generate structures that hopefully are a good explanation for your spectrum. And the convenient thing is that they are ranked the same way as all the other stuff is ranked. So even the de novo structures are just part of your one list of explanations. So yeah, you have to look into a different tab for that, but Fleming will show all of this later. Yeah, so then, like we now talked about getting the exact structure. Another thing you can do with CSI FingerID with SIRIUS is using a tool called Canopus, which allows you to predict compound classes. So it can predict the classifier ontology from David Wishart and also the NPC classifier ontology. And the idea behind that is that this is completely de novo again. So we do not look into any database there. So the idea is we can compute the fingerprint without looking into a database, and we can then, from this fingerprint, compute compound classes without looking into a database. And that means you can annotate your whole data set, no matter if you know what database to search in. And you will get at least, you will not get a full structure, right? But you get the compound classes for it. And this allows you like some different types of analysis. So yeah, so it's like about 2,500 classes, and this is like very, very accurate. and you can like then basically like make nice statistical like bird's eye view analysis on your data set. So you can basically like check how much of my data set belongs to which compound class and try to compare different conditions or organisms or whatever. You can also use it, for example, to annotate molecular networks. Unfortunately, like these two things are not built in. You can just compute the compound classes, but for everybody who is like a bit into Python or R scripting, we basically have since 0.6 a very powerful API where you basically like can just install the Python package and access all the data SIRIUS produces in like a very convenient way, which makes it very easy to like produce such results, as Fleming will show later. Yeah, maybe like as a wrap up, we have like the possibility to show you your library hits, which gives you like the full 2D annotation for the structure, but does not allow you to see novels, right? So that we get like also for unknowns results, we basically can do structured database search. We can like somehow also search for novels using structured database search if we like generating them combinatorial or using biotransformations or like using a generative ML model like MSNovelist. And there's the compound class annotations, which will not give you a structure, but work for all compounds that have or for all features that have like a decent MS in your data set. And yeah, both of these do not need a reference measurement, which is pretty cool. Yeah, so let's come back. That's basically like this full workflow, which is a lot of stuff. But the good thing is, in the software, it's not. This is like basically all parameters SIRIUS has you have to care about, and the large buttons are usually just to activate things. So there's not too much to set. The most important part is like specifying the ad hocs that are possible and selecting the databases you want to search in. And here's the part yeah, with the strategies. Yeah, so who is doing that? SIRIUS is developed by two groups now. So it's developed by the Böcker group from the University of Jena, and it's also developed by our spin-off company, the Bright Giant. And they are basically doing all the work. And now I think we are ready to do some live demonstration. Or maybe before, are there any questions before we start with live demo? Okay, perfect. Danke.
Okay, let's start. Can I make it a little bit bigger? Okay, probably. Maybe I can change it a little bit.
Sorry, I have to change the resolution quickly. So, I can do something right.
Okay, perfect. Yeah, welcome also from my side. I'm Fleming Kretschmer, and I will try to guide you through this live demo part now of the workshop. First, before we start, I just now already opened SIRIUS, so I hope this is working for everybody who wants to follow along. So you can follow along. There are, we try to provide data for everything, and also a text file with the examples that we will look at. So if you want, you can follow along, but also if you just want to watch the presentation, that's of course also fine. Okay, but now I hope for everybody that wants to follow along, it is possible for them to open SIRIUS. So this is what it looks like when you don't have any data. And the first thing that we want to do, especially if we want to make computations, is we want to log in. Now we provided a workshop account. I will just show this here very quickly. So everybody that doesn't have an account and wants to log in, I hope this is visible for everybody, but the link that you got in the email for the workshop preparation contains a link to this website where at the bottom you will find the credentials if you want to log in. So I hope everybody that wants to follow along is able to. And if at any time you have any questions or anything doesn't work for you, Markus can always help you. And also the other Markus, yeah.
Yeah, so if anyone has some issue in between, just raise a hand.
Also, if it wasn't possible for anybody to download the data, there's still some USB sticks if you want to have the data. Okay, but let's get back to SIRIUS. And so now we already logged in. For everybody that hasn't logged in, you can just click on this account button, and then you will be able to enter the credentials to log in. And ideally, if everything also works with the internet connection, you will now see in this dashboard view that there will be green arrows. So I hope everybody can connect to the internet. If it is not possible, it's also not super important, because most of the examples we will look at, everything will be pre-computed, so we don't have to do any computations ourselves. But if at any time you're using SIRIUS and you see that something doesn't work, it's always a good thing to check this web service tab. So if you click on web service here and make sure that there are always green arrows, so everything works and you are connected to the internet and to the servers and everything. Okay, but still this looks pretty boring right now. Nothing is in here. So let's load in some data. Let's open now everything that was in the Google Drive folder. And in the Google Drive folder, there are like some subfolders, and one of them is called Tomato MZML. And as Markus now said in the first part, if you want to import data, there are many formats possible for this. But if you load in full LCMS runs, the most probable format is probably MZML. And we now try to load in some data. For this, because it can take some time, this is all the preprocessing that Markus explained. Let's just select 2 of these MZMLs, and thus let's just drag them into SIRIUS. So you can simply drag and drop data into SIRIUS. If drag and drop doesn't work for you for some reason, you can also use the import button here in the top left. And then you'll be greeted with this dialog, which will ask you if you want to align your runs. And because we have just selected 2 MZML files, which contain multiple LCMS runs, we probably want to align them, so we have features that are aligned between the runs. There's also another setting, but this is probably not important for you. It's only to keep some low-intensive MS-only features. But yeah, for most purposes, you will probably just want to keep that as default. You will want to align your runs and then just click on import. This will take now a little while, so this is now doing everything that Markus explained. And as Markus said, you don't have to make any settings here. Everything will run automatically. While this is loading, let's look at some of the stuff that we have. So again, if I can go back. Oh, something is not working, but okay, now it works. So I just wanted to show you, if you want to follow along for the examples, there's this follow along text file. I will just open it now. And later on, when we go through the examples, you can just copy-paste the IDs. And if you get stuck somewhere, you can just get to the next ID. And hopefully, we will all look at the same thing together. So now the preprocessing has finished. Now some stuff has appeared. You can see this in the left side. So here, all our features which have been detected are listed. You can scroll through this list and see it's quite a long list. So although we have just selected 2 of these files, we still have a few thousand features. And this list is even filtered a little bit, because if you just look roughly at it, you can see like each of these is one feature. And in the top line, you have this feature ID, this number that you see. And to the left of it is this small circle. And the circle already indicates feature quality. So what you can see now in this first tab, in the LCMS tab, is a tab which will give you some overview of your data over the chromatogram, and will also give you some indications on whether everything looks fine in your data. There's like a simple traffic light system, so what you will see in the left, if this feature has now like a yellow circle, it will mean, okay, this is a decent feature, it's not perfect, maybe some stuff is missing, so maybe here the it is telling us that the fragmentation pattern quality, that there might be something that isn't perfect, but this is at least a decent feature. You always have some features which have a high quality, and this can already give you some overview before you start computing stuff, because if you have features which have just low quality, maybe you don't have any peaks in your data, it also doesn't make too much sense to compute something for it. Okay, you see, just to explain this a little bit, you can see here the chromatogram. What you can also see, if I move through this list a little bit, we just dropped in 2 MZML files. And you can see now here the intensity of the feature in the 2 different files. So again, we aligned them doing preprocessing. There's also, if I can find a good example, an overview about isotopes and adducts. So for example, here we also have isotope peaks detected, and we have some adducts which are correlated, which are highlighted here. But yeah, I'm not going to go into too much detail on this. Just one thing that I want to show is there's now, perhaps for people who have used SIRIUS before, but not the new version, there are now like some toggles in the top. And there are also some features which, where we would get like this red circle for the traffic light system, which we think there is not too much information inside, which we just say are bad features. And if you want to look at them, by default, they are hidden. But you can click on this toggle, and then you will also see, okay, here are some features with these red circles where something seems to be clearly wrong. Yeah, but we will disable this again and get to the normal view. Okay, now just to go through this in a little bit more detail, what you can see here at the top, again, the feature ID, then the detected adduct, if some adduct was detected, the precursor mass, the retention time, and then what Markus talked about, this confidence score, but because we haven't computed anything, we also don't have any confidence score yet. So let's get to the computation. Because if you just look through the tabs, everything here is quite empty. What you can see here, so what you can look at before you do computations is you can look at the spectra, for example. But yeah, the interesting stuff comes really when you start computations. So let's do this. This is one of the most important buttons here, this compute all button. And now, we already saw this in the presentation, this is the main computation dialog, where you have all the tools of the workflow. Markus already mentioned a few settings that might be interesting. So for example, in the top, you have these adducts, which you can change. Now, important thing about this is we try to detect the adducts when we do the preprocessing, so when we input the data, and these adducts will only be taken as fallbacks if we haven't detected any adducts. But if you want to enforce them, there's also a button for this. Now, the other important global setting for many of the stuff that we have below is the databases. So here, by default, all the biostructure databases are selected, but you can, of course, change this. And if you have custom databases, like Markus explained, you can also select them here. So for example, if you want to do spectral library search, you would want to enable your spectral libraries that you have loaded in beforehand. So I don't want to go into this about this in too much detail, but one thing that is also new is this bar for presets. So you have some presets that are already set. So for example, the default preset, database search preset, MS1 preset. Let's go back to the default preset. And you can also make your own presets and save and export them. So just a few more settings. So the first button that you have and that you can enable is the spectral matching part, where we can then look at spectra for validation to reference spectra. This, of course, only makes sense if you also have some spectral libraries here selected. For this, yeah, I don't want to go into too much detail, but you can, for example, select the precursor deviation that is allowed. Also, you can have a button, or you can toggle on and off the analog search. Now, SIRIUS is so this part here is where you identify molecular formulas, and the strategies Markus already went into in some details, so I'm not going to explain them now. But the recommended option is to do de novo identification and bottom-up search. But you can change the strategies here. So if you, for example, only want to search in databases, you can select this. But as Markus said, then you won't be able to identify truly novel formulas. But let's just stay with the default. One setting here which is important is that this mass indicates below which mass the de novo part will be turned on. So below this mask, we will use de novo, and beyond that, only bottom-up search, because de novo can result in some large runtimes. One setting which can also be important for you is the allowed elements list. So especially if you only do the de novo strategy, you might want to set some elements. So here are the allowed elements in this list here, and there are also some elements which can be auto-detected. So this is, I would just leave this at auto-detection, but there are some elements where this auto-detection is not possible yet. So for example, you know that you have some fluorine in your data, or you expect some fluorine. You will want to, I will just close it again to show this, so you will click on these 3 dots here, and then you get this dialog, and here with F for fluorine, you can now select how many atoms will be allowed, and you don't want to go crazy with this setting, because if you set a too high value, this also might result in large runtimes. Just set here some reasonable value that you might expect in your data. Okay, but let's just leave it as default here. Zodiac, Markus also quickly touched. The thing about Zodiac is you want to make it, you want to enable it if you have complete runs that you analyze, and what is important also, if your machine is capable on it. So if you have a machine that is not too powerful, you might want to disable it. If you click on Zodiac, it will also show you this warning. So yeah, you can click yes or no if you want to enable it or not. Okay, the next thing, so I don't want to go into too much detail, so this doesn't become overwhelming, but the next part is where we predict the fingerprints and also compound classes. So people who are more familiar with SIRIUS 5 or earlier versions, there were 2 settings for fingerprints and for compound class prediction. This is now 1 setting which you can turn on, and the only option for this is the score threshold. So this is the default, that you only compute the fingerprints and make the class prediction for the molecular formulas above a certain score threshold, but if you want to have more predictions, you might want to disable the setting. And the last thing is the search in structured databases, or also, of course, in your custom databases that you imported. And for here, the only thing that you might want to set is, and this is quite an interesting setting, so I didn't tell you this in the beginning, but by default, PubChem is not selected, and the reason is that we normally, we try to first find stuff in all these bio databases, which are selected by default, or if you toggle this bio button. And if we can't find a hit, we have this new setting, which we call expensive search, PubChem as fallback. And if this is enabled, if we don't get any good hits with the bio databases, it will then search in PubChem to maybe find a better hit. This is the confidence mode that Markus talked about, and we will see some examples soon on this. And last but not least, the MSNovelist button to make de novo structure generation. So I hope this wasn't too much. I just wanted to go over everything quickly. If you really want to change more stuff, there is this advanced button, and then you get a lot more settings to set, but let's not mess with this here. Maybe one thing to know is that for most settings you can, okay, this doesn't work, but at least for some of them, you can hover over the settings, and it will give you some explanations on them. And of course, I didn't show this in the beginning, but there's also this docs button in the main interface, and everything should be explained in documentation. Okay, but let's turn this off. And the last thing I want to show here is, if you now spend some time setting up everything that you want, you might want to save it. And one way to go about this is to click on this show command button. And this gives you simply the command that will be executed. And this might also be interesting for you if you don't have a very powerful laptop, or you just want to run everything on some compute cluster. What you might want to do is you might want to set everything up in this dialog, and then just copy this command. There's this copy command button also here, and then just run this on your compute cluster. And everything that you have set will be then executed as you wanted it. Yeah, there's also now this new show JSON button, but this also just shows you the settings, and you can maybe save them somewhere if you want. So now we are not going to click on compute because we don't want to spend too much time waiting, but normally you would then click on compute and wait on everything. But now we're just going to click on cancel, and what we're going to do instead is we are now going to load in a pre-computed workspace. Now in the workshop folder, what you have is this file called tomato_small.serious, and this is the project space that we want to look at. So in this project space, we made all computations already from all the MZML files, and what you can simply do, you can simply now drag this file into SIRIUS. But before I show this, the last thing I want to mention for this old dataset, if you now do your computations and you want to save them, there's of course the Save As button, because what you can see here in the title bar, it's a little bit small, but what you will see on your machine if you follow along, you can see that even if you just load in data, it will be saved somewhere, but only on some temporary location. So if you want to keep your stuff, you will just click Save As, and then you will set a name for your project, and then it will be saved. But now let's load in this pre-computed project space. We just drag and drop it into the window. Okay, this was not the thing I wanted. Okay, like this. So we have to drop it into the feature bar, but you can also just click on the Open button and then just select the .serious file manually. So again, we now just imported this tomato_small.serious file, and we want to open it in this window. So we don't want to make a new window, and this will take a little bit of time, but yeah, it will be really quickly. And now we have our new project, and again, it's quite small, but in the top bar, you will now see that this is the new tomato_small project that we just loaded in. And the first thing that you might see, I hope everybody who wants is able to follow along. The first thing that you will see, if it was possible for you to load this in, is that now in this feature list on the left side, a new row has appeared, or at least new values, and this is this confidence score. So because now we have done all the computations are included in this project space, we have now confidences. And this is also what Markus explained to you in the beginning. Maybe this is interesting to look at as a first glance. How confident are the annotations that you have? And maybe if you don't have time to look at everything that you have, and you don't want to spend time on looking at features where you can't get good annotations, you might want to look only at the features which has a high confidence score. And to quickly show them, you can now right-click on this feature list. So if you right-click, you will get this context menu with some settings. So for example, you can order this list by retention time, which is the default, or you can order it by mass. But what you can also do now, if you imported everything, if you loaded the project space, you can also order it by confidence. So we now just right-clicked and then selected order by confidence. And now we have the features with the most confident annotations at the top. So here you see we have a confidence score of 0.984. So it's a quite high confidence score because it goes from 0 to 1. And now we can actually look at some stuff. So now the interesting part really happens. Let's just select this first hit. If you really want to follow along the exact example, this example should end on 2707. But what you can also do if the sorting didn't work for you, you can just go to this follow along text file and just copy and paste the first ID and into the search field, and then just search for this ID. Now we will look at this a little bit at the different tabs, and the first tab that you have will be the formula identification tab. I will now just show this. So before we had any computations, we could just look at the spectra. But now we also have a list of formulas which have been identified and which are ranked according to their SIRIUS score, which is shown here in this column. And we have a fragmentation tree to each formula. Now the first thing that you would see if you would look closely at this, so the first column that you have, besides the rank of course, is the molecular formula itself. And what you might see is that these first 4 hits actually share the same molecular formula. The only thing that is different is the detected adduct. So if you just add the adduct to the formula, we'll get the same formula. And you will also see, if you just scroll through this a little bit, that the fragmentation tree on the right will look quite similar. And all the scores that you have in the further columns will also be pretty much the same. So the first thing you have is the SIRIUS score, which is used to rank these formulas. Then you have the isotope score, which tries to look at the isotope pattern, the detected isotope pattern, and the predicted isotope pattern, which you can see if you click here on mode on MS1 mirror plot. Then you will see in the top the detected isotope pattern, and in the bottom you will see the predicted isotope pattern. And this isotope score reflects how well these two patterns match. This is the first indication on whether our formula is good. The second thing that will be scored is the fragmentation tree itself, which you can see here. And if we now go back to the MS2 spectrum, what we can actually look at is now the different peaks and the subformulas which they are annotated. So if you hover over this formula, unfortunately it's a little bit small, but maybe if you try it on your own screen, you will see that in this hover window right next to my cursor, there will be the formula highlighted and also some other stuff. And what you can actually do is you can click on such a peak. It will then be toggled. And you can also see, so this, the spectra view and this tree view are synchronized. So you will see that now this fragment in the fragmentation tree has been highlighted. And you can even now click on another fragment in the tree. And you will see that then also the peak changed. And just one note on the colors, you will see that most of the peaks here are now blue, which will mean that most of the MS2 peaks we were able to annotate with some fragment of our fragmentation tree. And this is actually reflected by this explained peaks number here that we see. So we can see most of the peaks, if not all of the peaks, can be explained. And another important measure is this total explained intensity, which just sums up the intensity of all the peaks that can be explained. So maybe as a number to know, you want this, of course, to be as high as possible, and maybe if it's above 80%, it's always a good sign that the fragmentation tree fits well to your data. Okay, I am not going to go to the other columns, but now, we have the formulas which have been identified, and the second thing we will look at is the predicted fingerprints. So right now we haven't done any database search. So now we just predicted the fingerprint based on the MS2 spectrum and the fragmentation tree. And now we find all the substructures which our method thinks that that the structure of this feature has. There are a lot of substructures and molecular properties in general. So Markus explained a little bit what the fingerprint consists of, but some of them are quite boring. So what we can do, we can filter this list a little bit. Let's just increase the number of heavy atoms. And I can see this example I wanted to show. So if we click on this, we can see, okay, we expect our compound, whatever it is. So we haven't done any database search yet. We expect our compound to have this kind of ring system included. And what you can see here is if we have this row, we have the posterior probability, which is how likely is this particular property contained in our structure, and you also have the predictor quality, but I will show this a little bit in the next view. The one thing that I forgot to mention is that the formulas that you had in the list before are now in this horizontal list, and you can also scroll through them. Okay, now the next step is the compound classes tab. I'm not going to go into too much detail, but as Markus said, we also predict compound classes, and you can see the classes which are predicted. The main class here, or the main classes here, are the classes from the classifier ontology, and in the top row you will see the hierarchy. So the most specific class that we predicted is this of spirosolanes and derivatives. You might want to remember this a little bit for the next step. Here's the description of this class, but of course a compound can belong to many different classes, and all the classes that are possible that have been predicted are shown in this second row. And what we also predict is these natural product classes, which is an alternative to classifier. But not too much detail on this. Now let's go to the next step, and Markus already showed you a preview of this, and probably this is the tab you will spend most time in, or at least it's a tab that is quite important. And now we actually have done our database search, or structure database search, and found some hits. And these hits have been ranked, so we can see in the top we have the hit with a rank 1, and the score by which this is ranked is this score below, so -12 and -197 for the first two hits. So you don't get confused. Higher is better, but because it's a negative number, the closer it is to 0, the better in this case. So -12 is quite a good score for this. And what you can see here, so you get the name of the compound that has been, that is our best hit, its molecular formula. You get the structure of this, and now you also get all these green dots, which are all the substructures which we have predicted. So all the ones that we have predicted in the predicted fingerprint tab, and that are also contained in this structure hit. And it also tells us whether these substructures fit or not. So here we can see we have many green squares, and a green square means that this particular substructure, which is contained here or if we have another example, this substructure was predicted to be present, so this is a very good sign. But if we had, for example, such a red square, so we now go to the second hit and just click on this, which will highlight this part in the second structure hit, this is something that we didn't predict to be there, so this is a bad sign if we get a lot of these red squares. And what is also important is the size of these squares. So the larger the square is, the higher the predictor quality is. This is just this F1 score, which is in the last column of the predicted fingerprints. And if you just have some small squares, these are predictors which are not too trustworthy, which don't have a high quality. So if you have some small red squares, it doesn't matter too much. What you can also do to get a quick overview is you can right-click on a structure, and then the first option will be highlight matching substructures, and it will just give you an overview on everything that matches. So if we repeat this with a second hit, we will see that here it doesn't look as good, so we can see this part seems to fit quite well, and this part doesn't fit, and the middle one, yeah, we don't really know. Okay, so this as a quick overview. Markus also explained a few other things of this. So if we have a hit in a reference spectrum, which I will show very soon, we can also see this here. Here we have all the databases where this compound is contained. Because we did a database search, we now get, for example, HMDB, KEK, and all the structure databases that this compound can be found in. And actually, because it's often a good thing to also verify a little bit more, we can click on such a box. So for example, we can click on HMDB, and I hope this works now. Because what I didn't tell you, but what was probably visible by the name a little bit, the data that we have imported is from a tomato dataset, and also the hit that we have now found is tomatidine. So this seems to fit quite well. And if we go to the tomatidine page in HMDB, we can see, for example, one thing I want to highlight is that this compound belongs to the spirosolanes class, which is also the one that we found in the compound class prediction tab. So this is a good sign that this matches. And what you can also see, this compound is found in the stems and leaf of tomato plants as well as in the fruit. So it's always nice to just look at this a little bit and see if it matches with your expectations. Okay, but now let's close this.
May I just interrupt for a second? Just one short interruption for an announcement. Some of you seem to be having like scaling issues with, like, for example, LCMS view or some Spectrum browser view, which seems to be specific for the version that was provided today. And it seems to be fixable if you just in your Windows settings change your default setting from scaling from 125% to the 100% again. Then also in SIRIUS it will be like visualized normally.
Yeah, so if you have Windows, there will be the scaling setting. Yeah.
Yeah, basically that's, so if you have this issue, just update to 100%, it should work.
Okay, now we look a lot at this particular compound tomatidine and see that it fits quite well. What we have here is now, besides all of these structured databases like HMDB, we also have some yellow boxes, which are actually for custom databases. So now I will show you how to import these custom databases, and what you will also see is you will have this 95% hit for this database called mass bank names, and this is hit in a spectral library. So this I will also show how to import these kind of databases. And for this we are just going to click on this databases tab, and now we can create new databases or import existing ones. Just to show this very quickly how you would create a new one. But in a second, we are going to just import some existing ones. But if you want to create a new database, just click in the bottom right on this plus symbol, and you will get this screen. You can give your database a name, a location, so wherever you want it to be stored. And now you can just drag some structures in them or some spectra. So just to show one example, in the folder you have the subfolder called custom DBs. And if you open this, there will be, for example, this file named tomatidine biotf input tsv. And if you open this somewhere, I hope I can open it with some editor, yeah. This file actually just contains the SMILE strings of the structure, and we will just now add this file to the new head to this window. If drag and drop doesn't work, you can also use the plus symbol here. Okay, now we would create a custom database, but this custom database would only contain one structure, this tomatidine structure. So the smile string I just showed was from tomatidine. So this is quite a boring structure database, especially because we already found tomatidine. But what Markus already explained to you is that you can use biotransformer 3 now to compute some transformations of your compounds that you have. If you know biotransformer, you can select the different transformations that you would want to apply. You also have some more settings here, and you can set the number of reactions that you want to perform. And if you do this, now the custom database will not only consist on the structures that you have put in at the beginning, but also will consist of all the transformations that you have made with biotransformer. So we,
can I have a question?
Yeah, of course.
Sorry to interrupt. If I want to integrate my own database or in-house database, for
Yeah.
example, what format does it need to be?
So what I just showed you, if you have structures, it will just be a TSV file. So just a text file, tab separated, but as I just showed you, like this example file is pretty much just the smiles, and that's it. So just a list of smiles, so each line should be a smiles, and then it should be fine. I think you can also give each compound a name if you specify it in another tab. Yeah.
Okay. And you can also have like SDF.
Oh, yeah, right, yeah. I didn't show you this, but if you click on the plus sign, it actually shows you. So now you can select structure files here, and it will show you, okay, TSV, CSV, or SDF, it's currently supported. Okay, so this, now we would have created a database for these biotransformations of tomatidine, but let's not do this right now live. Let's just import the one that we have already created, and for this you can just click on the second button here, Add Existing Database, and then just navigate to the folder. This would be in the custom database folder. This would be this tomatidine biotf structures.seriusdb. So .seriusdb is the extension for existing structure database, or also a spectral database, as we will see soon. And if we open this, this should be, this is pretty much instant. You will now see this is custom database is also inside, which now contains actually 1,100 compounds. So with this biotransformer, we really added a very big list of possible biotransformations of this tomatidine structure. And let's also now add our other custom database, and this is our spectral database. For this, if you want to create it anew, I'm not going to show this now, but you can just import the spectra if you create a new database. But we have one already made, which will be the one mass bank name spectra.seriusdb, and we will just open this. And if this, we have opened this, this will now be our second item in this list. And we can see this mass bank names actually has a lot more compounds and close to 100,000 reference spectra. So now we have these databases, and I will now close this, this window here, and we'll just refresh the view. And what you can see now, if you look very closely, is that these boxes now are now active pretty much. So what you can, for example, do now is you can click on this show more beyond the or below the reference spectra result. And if you click on this, you will now get substructure annotations view. I will explain this very soon. But what you have pretty much here is like all your MS2 peaks, and now you don't only have blue-colored peaks. Blue-colored means that you have a fragment in your fragmentation tree which can explain this peak. But now, because we did our combinatorial fragmentation of this particular structure hit, so this is something extra. This is not something that we always do, but this is only for your validation. And if we now click on such a peak, we can see that the substructure which matches to this peak, so this is now not subformula, but a substructure is highlighted in this window. But what I really wanted to show you here is that you can now select the library hit. If it worked for you and you could import the spectral library, the mass bank spectral library, you will now see a list of spectrum of reference hits, and you will see the name of the spectrum of the compound from the spectrum in the first column, then the cosine score, the number of matching peaks, and also some delta mass, which I will show some example very soon. Yeah, I still have enough time. We will now just click on the third hit here because all of these hits have a high cosine score of even higher than 0.9. And if we click on this, we now also have such a mirror plot, and in the top you will see your spectrum, and in the bottom you will see the reference spectrum. And now you can compare the spectrum that you have with the reference spectrum and see if everything matches and everything looks okay. And what you can also do is you can still go through the peaks. What you can also use to make this a little bit easier, you can also use the keys on your keyboard to switch between the peaks, and you will then see that all the parts in the structures will be highlighted which match to these peaks. Okay, but now let's go to another example. Now I showed you this tomatidine, so this is quite boring because tomatidine, we of course expect this to be in such a tomato data set. Let's go to a more interesting example, and what we do with this now, and what I haven't showed you is that you can also filter your whole list of features by some criteria that you define. With this, just to show this a little bit more slowly, you just click on this ... in the top left, and this will open the filter panel. And here we can change or set some things. For example, you might want to only show features in a certain MZ range, which you can set here, or in a certain retention time range, or like for some certain adducts. But what you also can do is filter by data quality, which is actually the default. So by default, we hide the bad quality features. But more interesting, you can now filter by results. If we go to this last tab, you can, for example, filter by confidence. If you only want to show features above a certain confidence, for example, I think still one of the thresholds, or like one of the numbers that you might want to use is everything higher than 0.6 is maybe like a good hint, at least, that this is a good feature where you get good structure hits. But yeah, you can select whatever you want here. You can also filter by molecular formulas. And what I wanted to actually show here is that you can now filter by hits in structure databases. So if it worked for you and you could import this tomatidine biotransformer database, you can now select this database here. It will check only the first candidates. If they have a hit in the structure database, you can change this here, how many candidates have to fit, or which candidate has to fit, the top 1, top 2, top 3, or whatever. And if you selected this, you can now just click on apply. And this will take a little bit of time, but not too long. But what it did now is it now filtered our feature list by only features where we have a structure hit in this tomatidine biotransformer custom database. And these should be now 9 hits, and I will now go to one other example. And if you want to copy paste this will be a second one, but don't worry, the following examples I will show much more briefly. Let's just so if the filtering doesn't work for you, you can just copy paste this, but we know, so this feature I wanted to show ends on 187, we can just find it in the list and just select it. And what you might see, because we now looked a little bit at this tomatidine structure, you might see that this tomatidine structure is also present in this particular hit. So this is the structure of tomatidine that we had before, and you have this added part to the left of it. And what you can now actually see, we don't have any reference library hits, so we don't have one spectrum which fits exactly to this compound, but what we do have is an analog hit, and this can be another validation for you. So maybe before I show this, as a repetition, you can still, of course, right-click now on this and make this highlight matching substructures and see, okay, most of this seems to fit quite well. Also, you have a high confidence score for this feature, but to get more validation or more confidence on this structure hit, you can go now to the substructure annotations tab. You saw this a little bit when I clicked on more in the previous example, but now again you have your MS2 spectrum with all the peaks which for which our combinatorial fragmenter could find an explanation, so a substructure which fit these peaks. And what you have now in this list, if you click on this, you don't have like an exact hit, but you have some hits have a high cosine score, so about above 0.8, and which have this delta mass, which means we don't have an exact hit, but an analog hit where the mass, where we have some mass difference. And if we select some of these examples, let's just take this one. What you can see now, or what you also saw before in this list, this is again the spectrum, the reference spectrum for tomatidine. and you will also now see again this tomatidine structure in the bottom, and you can now compare the spectra that you have for this structure, which is not tomatidine, but tomatidine with some part added to it, and tomatidine, and you can still now click on the peaks and get the explanations for your particular substructures and see if this fits. So maybe at a quick glance you would see that this left part seems to fit quite well, and here we have some peaks which don't fit, but they would kind of fit, because here you just have this loss of this hydroxide group. Yeah. Okay, let's now go to another example. And this will be really quickly, because this will now be an example. You can copy paste this, or I will just also get it in this list, because this is still in our custom database for biotransformations of tomatidine. And let's now go back to the structures tab. And what we can see here now, so we have 3 hits which are highlighted in green, which means that these hits are really similar from the structure. And because we use this approximate confidence score and not the exact confidence score, we are now only interested if the first structure or a very similar or a variation of this structure is a confident hit, which you have here. So you will see here, if you look at this a little bit more closely, that these structures resemble one another quite much. The only thing that is changed is the hydroxide group, which is at different parts of the structure. What you will also find, the interesting thing is that these 3 hits we can only find in our tomatidine biotransformer custom database. So these are not included in any kind of public database. Okay, this is one I wanted to show here. You can still see if it matches, and it seems to match quite well. Just as a quick repetition of the example before, we can still do our analog search and find out, okay, we still have a very good hit to tomatidine. Let's just select some of these. Yeah, and you can now compare the spectrum of this compound with tomatidine again and see if it matches. Okay, now we looked at MAF tomatidine examples. Now let's look at another example where we now will leave our custom database hits. So maybe this is one thing that is important to know. We have now filtered our feature list, and if you want to discard the filter, you just simply click on this ... next to the search bar. This will open the filter panel again, and you can click in the bottom left on reset, and this will reset all your filters. And don't forget to now click on apply, and if you click on apply, you will now still get your original list of all the features. Okay, now let's I will just copy and paste the next feature ID to go through this quite quickly. We look at this one. This also has a high confidence score, 0.98. And if we look at structures, we will see that there's now a red banner. And I just wanted to show this very quickly, because this is an example where we have performed this expansive search. So we couldn't find a really good hit in our default selected biodatabases. So the best hit in our biodatabases would be the 3rd one, but we have found a better hit in PubChem. But we didn't search originally in PubChem. We just had this option that if we don't find any good hits, we will then as a fallback search in PubChem, and we will get these hits now, which seem to fit quite well. Okay. Yeah, we have still a little bit more time, and one example I want to show where we will now actually compute something and look at the last tab, which I haven't showed you before, which is this example. So I now just copy-pasted the example, which ends in 767, if you want to follow along. And if we look at this and look at the structure tab, we can see, if we just look at the squares a little bit, we can see, okay, we have a lot of red squares. Also, the confidence is not very high, 0.4 is not a high confidence score. And if we right-click on this, highlight matching substructures, also some parts don't really seem to match. And what we can do in this case, if we can now actually perform this de novo search, we can now compute de novo structures with MSNovelist, and we will try to show this here now live. We'll just right-click on this compound, and the first option you have is this compute option. And if you click on this, we now have our compute panel again. It looks a little bit different because we are now just doing computations for a single compound, so you don't have a Zodiac button here, for example. But the only thing that we want to do here now is turn on this MSNovelist button to perform de novo structure generation. So we just click on this. We'll get a warning, do we really want to do this? And we want to. And what you want to make sure, because we already have computed fingerprints, we have identified formulas and so on, we want to make sure that we don't recompute everything that we have done already. So you want to uncheck this recompute already computed tasks. So make sure that this checkbox at the bottom left is disabled. And if you have enabled MSNovelist, you can click now on compute. And what I can show you here now, what I didn't show you before, is you have this jobs button where you can see whatever computations you perform, how the progress is, how long, how far it is in the computation. While this is computing, what I can also show you, what I didn't show you before, is this log, which can be quite important. So especially if you get some errors, you might want to open this log panel and see if you can find something, maybe some error message that will tell you something, maybe whatever you imported didn't work, maybe you just imported a file which doesn't have any content, or maybe whatever went wrong, it probably is in this logs panel. Okay, I hope it doesn't take too much time anymore, but maybe I can click on this already and show you something. So what will soon appear now is in this de novo structure tab, we will then hopefully get some de novo hits. And what you will then also see, but I will wait on this. I think it shouldn't take too much. Yeah, it's already perfect timing, so it's now finished. We now have our de novo hits, and these are in this de novo panel. And what you can see here, these seem to fit a little bit better. So just as a very quick first validation, you can right-click again, highlight matching substructures. Okay, most of this seems to fit. And if we now go back to the structure tab, not this, but if we stay in the de novo structures tab and just scroll down a little bit, we can see that our previous best hit is now at position 20. So we now got some new hits with MSNovelist which seem to fit our structure much better, and these hits are not contained in any database, in this example at least. Okay, we still have half an hour, and I want to show you, I think we have a few more examples. Yeah, one example I can show you very quickly is there's now the option for homolog series that you can detect them. We will just copy and paste this feature ID. And before we can look at something, I just want to show you, you will have to enable something, and that is in the settings panel, which I haven't shown you before. So if you click on this wheel, this gear, you have a settings panel, and you can select some options. So for example, you can toggle the default confidence core mode. You can, for example, what I haven't showed you before, but this is also new, and there are now some tours. So if you start SIRIUS for the first time, probably this happened to you. You got like some dialogue which said, do you want this tour to guide you through this particular panel? And maybe you just clicked skip, but this tour you can actually also enable them if you disabled them before. But what I really wanted to show you is there are now two settings: show homolog series tab, which I will now enable. And again, if you want to follow along, I will now look at this feature which ends in 482, and now look at this new tab which appeared, homolog series, and this is a Kendrick mass defect plot. And here you can look at potential homologs in your homolog series. The setting that you have for this is the repeating unit formula, which you will have to adapt if you are interested in a particular homolog series. But yeah, you can now just hover over these dots. And what you can also do is you can right-click on one of them and directly jump to the feature if you want to look at the feature in this homolog series. Okay, but now something else. So I don't want to show these additional examples, but because maybe we can leave some time in the end for some questions. One thing that I want to show, and that Markus already talked about a little bit, is that there is now an API which is quite powerful, and especially if you want, because the title of this workshop is also automated analysis, and now we looked at SIRIUS and looked at all the different panels, but sometimes you just want to get a brief overview on whatever you have in your data, and beyond just going for high confidence hits, you can also use the API for this to make some data analysis. Before I will show you this, you can also export whatever you have computed with this summaries button here. So there are some settings that you might want to select, but yeah, the top hits will then be exported to whatever location you specified. There's also an export for the feature-based molecular networking from GNPS. But now to the API, and I just want to show this very quickly. It might also be that a lot of you are not interested in this, but people who want to script a little bit, if you go to the settings button, in the bottom you can see this open API in browser, and if we open this, you will just now in a few seconds get an overview on all the API functions which are exposed and which you can use. But yeah, I don't want to go into this in detail. This is a little bit interesting if you want to see what is possible and if you just want to try out stuff. So for example, you can just click on something and click this try it out button, and then you can just really try out what output you would get for a particular input. But of course, many of you who do scripting would then script something in Python or maybe in R, and there's now an API available in Python and in R. And now let's look at this. There is another file in the files that were provided, and that is, if we go to the top folder, this workshop API demo.ipynb, so this IPython notebook. Yeah, you might be able to just double click on it to open this if you have IPython installed, but I just want to show this very briefly. It is now actually quite easy to just access the API. So what I do in this example is I have just started a SIRIUS instance. Sorry? Ah, yeah, yeah, can zoom in, of course. Yeah, to make this, of course, it's a little bit small. Yeah, but this is now just a Python notebook of Python code. If you click on the first link, there's also, I hope this opens a second tab. Yeah, there's also here a link to the GitHub and instructions how to get the API installed for R, for example. But now let's go back. And what we will now just do is attach to the running SIRIUS instance. And this is just the first block. So whatever we have started now, the project that we have just opened, will now be available in Python. If we execute this code, so we just import PySirius and then just attach to SIRIUS. Now, it might be that you have multiple projects open, but for this we will just open the first project that we have with this box. And I just want to show you one example. That is, of course, so let's just go briefly back to SIRIUS. You can export everything with this summaries button, but everything that you have also available in the API. And this is what I will do here now. I will get all the features that we have found with this code snippet. In the next snippet, I will just filter out, or I will limit myself to only features where we have some computations done, where we have computed compound classes. So we are now going to look at compound classes. So these are all the features where we have compound class annotations for. And now we are just going to collect them in a pandas data frame. So if you use Python, you're probably familiar with pandas. And now we have a nice data frame that we can look at. And of course, we can also make some visualizations. And for this, I just have a quick example which uses Plotly to make such a sunburst plot, which we see now at the bottom, and which can give you just a very basic overview on whatever you have contained in your project space. So these are the compound classes that have been detected. And in this sunburst plot, you can also click on something. And for example, if you hover over this, you can see, okay, for this triterpenoids, we have 51 features which were classified as this class. Yeah, but this might give you just a basic overview, and of course you can do much more stuff with this. And maybe this API is also much more interesting if you want to do some manipulations. So what you can do in the API is also delete something, for example, so you can manipulate everything. You can do a lot of stuff that you can do in the GUI, you can also do with the API. Okay, now I have actually quite a bit more time, so I can also look at some of the additional examples. Let's just go through the first one. Okay, this should be, okay, this was already the homolog series. This is maybe an interesting example where you might be a little bit careful, because I told you before, it might be that in your structures tab, you have multiple hits highlighted in green. And why are they highlighted? They're highlighted if the structures are really similar. We use an MCS distance of up to 2 to highlight them. And what you can see here, the structures are really quite similar. What is a little bit weird in this is that you also have this ring structure, but except for this ring, everything looks quite similar to this. But yeah, this is just something that you have to keep in mind. And maybe I can show this now. Everything that we looked at before, so all the confidence scores we had, was the approximate confidence mode. But you can also switch to the exact mode, not only in the settings window, but also if you right-click on this. And here somewhere, we have used exact confidence mode. And if we switch to this, it actually is really quick. And now we get the confidence score for the exact hit, which might be a little bit different. But what you will see now is that only one of the structures is highlighted in green. So again, like Markus said, exact confidence score really means how confident are we in the top annotation, the top 1 annotation, not in structures which are similar to the top 1. Okay, I think I have one more example, but this is actually quite boring. This is just one example where we don't have any commutations, where you should be a little bit careful, and that is if we now go to the formulas tab and to the MS2, we can see we really only have one peak. So of course, like these kind of features, if you encounter them and if they haven't been filtered out by filtering out bad hits with these toggles here in the top, for this you will probably not expect a good structure hit, and in fact we haven't even computed structures. So just be careful with whatever you look at. It might be that the features are just bad. You don't have any informations in your spectra, so you can also not expect good hits. Okay, but I think this already brings me to the end. And I would say we now have time for some questions. So I think if you have something to ask, there are also mics at the sides. Yeah.
So right now it's only CID. We are working on HCD right now. Looks promising. So like in the other workshop right now, Nicola Zamboni has tried a bit, and it already, like with some minor modification on the scoring, it works quite well. EAD. So EAD. Sorry for that. I can hear you, yeah.
Okay. So the first question that in our work we are looking also at environmental contaminants. It's pretty common that we have, for example, chlorinated compounds, more than one chlorine. And then I was wondering if you have any recommendations in terms of the selection of the elements. For chlorine, is it better to just leave in the auto-detect, or should I include in the element? Is there a difference at all?
So I mean the elements that are in the auto detection list you can just leave as auto detect. So it's really like to specify them on your own is usually only possible if we cannot auto detect them, and or if you're like particularly sure that something has to have a certain element or something like that.
If I may have another one.
Yeah, sure.
At the beginning you briefly mentioned the sensitive mode. Because we are also many times interested in very low abundance compounds. So what it does exactly if I choose the sensitive mode?
Yeah, so we basically like have an automated preprocessing, right? And so we basically like just lower the thresholds for the noise and some other things. It's just like that, like the usual noise detection would like filter very low abundance features out, and like in case you are dealing with some specific data set where this is important that we do not do that, like in a preprocessing focused tool at MZMine, you would adjust it by yourself, and here we basically have these two modes, do it normal or do it very, very sensitive. Yep.
About the fingerprints that you saw at the beginning, which is a foundation of the model. You usually think TCFP6, do you think it's okay? Are you trying to use something else better develop, or it's good and we trust because it's a foundation? foundation of the model. And
Yeah, yes.
how well we can.
Yeah, so what we are doing is basically that we, maybe I can even like show it in the software a bit. So I need a nice example for that. So let's check, yeah. So what you can basically see here is all the molecular properties we are using, and they are basically derived as part of the training process. And there are like well-known fingerprints, for example, like from PubChem or Glycota Rot or Max or also ECFP. And there are also additional combinatorial fingerprints we basically derive, or molecular properties, not fingerprints, we derive from our training data. So we basically take our training spectra, do combinatorial fragmentation on it, and build properties that match these fragments. So it's like a bit, it's like a long mix, or like a big mix of different molecular properties. And we only basically include molecular properties in the fingerprint of a specific CSI FingerID version that can be predicted with a certain quality, right? So we do not insert fingerprints where we are not able to train a predictor that has a certain quality. Does it answer your question? Yeah?
So I was wondering, when we do our preprocessing, usually in MZ9,
Yeah.
we have positive ionization measurement and negative ionization measurement, and we usually like to merge them
Mm-hmm.
and use that MGF that comes out of that to use in SIRIUS. So we have negative and positive, both red.
Mm-hmm.
I was wondering if this confuses Zodiac in some way, or if this is, because I never got a satisfying answer when I was looking for this.
Yeah, so Markus, maybe you can comment on that. If you think that has makes a problem in general, as long as like the features are like have the correct adduct assigned, mixing them in featureless data works. We cannot like preprocess them together right now, but if you get your preprocessed data from MZ9, it should work. Markus, can you comment on Zodiac?
In general, I would assume that it just works because the idea of Zodiac is that if you have some related compounds in there, it should be also between positive and negative mode, because if you have like a metabolomic sample, then these compounds should be related. In principle, it should work, but I don't know if there
I
are
was wondering specifically because sometimes you might get compounds that are ionizable in both modes, and sometimes you don't. And then maybe it skews the ranking, the ranking.
you include some bias, you mean?
Yeah.
I mean, I never looked at it basically. It's a very special case, but in general, I would expect it to work in this way. Yeah. If not, we probably need to look into detail more than that.
There was, yeah, I think over there.
So thanks from the workshop. My question is in relation to the scores. So do you have any values that are reasonable to get in relation to the CSI score that you say it is close to 0, it's better, but sometimes it has different values like -6,
Mhm.
-80,
Yeah.
-150.
Yeah, yeah.
Rule or any suggestion
Yeah,
in relation to this question?
Very, very good question. So regarding the CSI FingerID score, it's basically locally. So the CSI FingerID score is not comparable among different features. So you can basically not define a threshold like saying everything larger than -14 is a good hit. That's why we built the confidence score. So because like the CSI FingerID score is very dependent also on the molecule size, which elements are contained and stuff like that. So this is really just a score you can look at for within the candidates for one feature. And the other thing is that something you might want to look at is whether your top hit candidate has a large gap to the next candidate. So this is already quite a good sign that this might be a good candidate. But to be honest, these are all features that are used by the confidence score. So we basically built the confidence score for that, right? It checks, does the compound class fit, is the score difference high, and so on. So yeah, so as a recommendation, don't look at the CSI FingerID score to check whether annotation is correct. Look at the confidence score. And for the confidence score, we at least found in our evaluation in the Cosmic paper that I think confidence above 0.6 corresponds to a false discovery rate of 10%. And like there's also a plot that where you can look at to get like some thumb rule.
Thank you. So in terms of reporting, so if I am using SIRIUS for and I want to report the results in a paper, so which score would you recommend to report, or which values?
Yeah, I would recommend to report the confidence score, and yeah.
Okay, thank you.
So there was another question over there. Yeah.
So in my work, I investigate the interaction between plants and fungi. Plants tend against fungi that produce phytophthis, so C-phytophthis, and the fungi produce sesquiterpthis C-phytin, and it happens that these molecules blend, and so we have this C-certified. So if I use Canopus, I get the annotation tritophin, which is C-certified, that's wrong. So if I need, because it's C-certified, so it's a mixture of these two groups.
Mm-hmm.
So if I know upload this new version, number of smiles, would that improve the annotation in Canopus, or would that not be affected?
No, it would not be affected. So the whole like idea of Canopus is to do not take into account any like structures, but try to annotate de novo just from the fingerprint. Yeah, please. Hey. Mm-hmm. Yeah, so in general, like the CSI FingerID idea is not like the best idea for annotating lipids. And what we can do, or what we have done at least, is we have not covered that in the workshop, but there is a tool called El Gordo, which basically, yeah, wait, I will just filter and look if something comes out. Let's see. I want to filter by lipid class. Where is it? Here. Yeah, it might take a while. However, so in general, we have a tool called El Gordo, which basically tries, before CSI FingerID runs, to detect whether MSM spectrum might belong to a lipid. And if this is true, it basically runs a rule-based lipid detection like you know it from other lipid tools. This is like still a bit in early stages, so I think we do not yet support all the lipid classes you might expect, but at least, I mean, the most common ones we have. And what it basically will do, it will not change anything on the CSI FingerID routine. CSI FingerID will still run. The only thing we basically do is that by the rule-based lipid annotation, we will find a single formula that works. So we do not have to rank multiple formulas anymore. And then we take this formula and run CSI FingerID. And it will basically show you the lipid class detected up here. And what it does then is it searches in the result list if some of these structures belong to that class and basically flags them by this blue lipid class tag here, so that you can basically see, okay, I know now it's this lipid class, and some of my candidates belong to this class. So that's basically what we can do right now to help you with annotating lipids. Yeah, please.
So, yeah, sometimes during the pick picking, double charged ion can be picked, and then you also mentioned that SIRIUS works only with single charged ions, and then in molecular networking, sometimes I see that that ion is in the network of certain class of compounds, but I don't have any information from SIRIUS. And then what I usually do, I can inspect the raw data as well, and then I find like a single charged ion for that molecule. And then I wonder if you know like any way how can I add that single charged ion to the whole data set for SIRIUS so that I can
Yeah, so I think now, oh wait, is it multiple charged or only dimers? I'm not sure right now. So we are currently like working on improving the support. And the general idea is like it will not be tomorrow that we can like really annotate multiple charged or dimers. But what we try to focus on first is that we like, since if you do the preprocessing in SIRIUS, or if you like can provide the data in a format that like different adduct species are grouped together, then the idea is basically that, because usually for small molecules the single charged ion is the most intense anyways, and you usually also get the best spectrum out of it. So basically if you can group the different adduct species together, then you can basically annotate the single charged ion and propagate the results to the multiple charged ones. And yeah, and right now, like with future UI updates, there will be the possibility that you can like see the groups, but this is nothing that like will be in the next version. So.
Okay, but there is no way right now to add, for example, one MZML file, and then I do like a whole, compute the whole SIRIUS, and then add it to the,
Yeah, sorry. So I'm not sure if it's in this version that it already works for multiple charged ones, but in one of the next versions we will at least find them in the preprocessing and add them to the project, but skip them during annotation. And like in the preprocessing view, you can then basically also check whether they are grouped together, like in the adduct network.
Okay, cool. Thank you.
You're welcome. So, are there any further questions? Yeah, please.
So, if we are working with the human serum plasma,
Mm-hmm.
and if we know there is still a person having some kind of infection from bacteria and fungi, so can we be able to detect those kind of infection or bacterial metabolite or the fungal metabolite in that?
Let me think if I got the question right. So, I mean, to like check for an infection, you would like do some comparative study, right? Or and like we do not yet do any statistics here. I mean, in the future, we will be able like to mark your runs, whether they belong to one or another condition. But in general, like you are not limited to a specific realm of compounds or something like that. So it doesn't matter whether they are from human or from the fungi. Is that what you mean? Yeah. So SIRIUS doesn't care about like what's the source of the molecule. It's just by the selection of the database where you restrict the search space. And in our biodatabase, we basically like, it's not really a biodatabase. I have to be careful with saying that. So it's like more or less, if you hit bio here, we will basically, it's also like the default, pre-select all databases we like think are of biological relevance. And they are like not specific for humans or something like that. So it really like just depends on what database you select. If you select databases that are like fungi related, then you can find fungi related compounds.
And how likely it is to provide wrong annotation if it is a confidence interval of 0.8?
The only thing I can now say from the top of my head is that 0.6 is 10% FDR. And like then 0.8 is less. I also have to look it up. So I mean, it's that's like, oh, do I have it here? Maybe I have it here. Let's have a quick look. Unfortunately, seems not to be the case. No, I don't have the figure here. Yeah, but like it's basically like the cosmic paper from 2022. There is the evaluation how the confidence score corresponds to FDR, and I think that's usually like where you can look which amount of error you are willing to accept, basically. Okay, if there are no further questions?
Ah, there are.
Oh, there are? Oh, yeah, sorry, I haven't seen you. Please.
Yes, thank you. Thank you for the nice workshop. So I wanted to ask, we have talked a lot about the confidence score, but what about the SIRIUS score, and in which situation would you look at it more than the confidence score, or if there is any?
Yeah, so in general, like for you as a user, there is like not a good reason to prefer the CSI FingerID score over the confidence score. So the confidence score is basically like saying you how sure is the software about the result, and the CSI FingerID score is basically like the measurement we need to produce the result. And as I briefly mentioned earlier, it's basically the CSI FingerID score is really like locally, it's just comparable within the results of a feature, and it's not like comparable over like a global scale. So it's like a local score basically. So like a score of -200 can be a very good score for one feature, and it can be a very bad score for another feature. So that's why we basically developed the confidence score, because the CSI FingerID score is not good in differentiating results on a global scale.
Okay. Hi, thanks for the presentation. You mentioned at some point that it's possible to upload your custom database or a spectral library as well. And I was wondering, like, how do you do that? I have a spectral library that we created in-house, and we have like an MGF or MSP file in which we have smile codes and we have a spectrum, MS2 and intensity for all the ions. And if I upload it, will be in the software already there, and I don't have to upload it like several times?
No, right now?
Yeah.
Okay, maybe that's so it's not like that you are uploading your data right now. Right now, the custom databases are locally on your system, so it's the SIRIUS DB file, and during import, we basically compute everything we need to search in this database. And then it stays on your system, and you can share the file with your colleagues, but there is right now no server storage for your structures.
And I do it through the import button, right?
Yeah. Yeah, so the import is basically here.
Yeah.
And like there are two options. Either you are opening an existing database, which, are there some here? No, I have no here. Doesn't matter. So, which is basically just adding it to the software that it knows it where it is. And there's the other thing, which is create a database, and then you would give it a name, say where to store it, and you drag and drop your different file formats that are specified here. So it's really like, for structures, you just have TSV, and for spectra, you have the typical spectral library formats. Okay. You can, yeah, they are all listed in the documentation.
All right, thanks.
Okay. So, yeah, one more question?
Sorry, related to that. Can you explain the difference, because I played around with this, importing your own database. So I can see there's three different flavors you could have. You could have structures only, structures and spectra, or spectra only. Can you explain the difference?
Yeah, so it's not really, it's just, so I think what you mean is basically this, right?
Yes.
Yeah, so this is just like for you to find your files easier. It's just like categorizing the file formats. It's just saying, am I looking for a structure file, for a spectra file? But our database in general does not really care. You can just like throw like a wild mix of all of these files into it, and it will basically like sort out which is which and generate one harmonized database.
So if you use a spectral database without structures,
yeah.
they're the complete unknown to what they are. How is that treated then? Presumably you can do spectral matches. But
that's something I will talk on Wednesday about. So what we are doing is, since CSI FingerID is like so good or as good as spectral library search in like finding reference database hits, we basically only search in structures. And the only thing we do is we ensure that CSI FingerID, since like CSI FingerID has like needs to know the formula before, right? And like library search does not. And what we basically ensure is we do the library search to ensure that no hit gets lost before ranking. And then we rank everything by structures. You get a single ranked list. You do not have to merge results. And on the ranks, on the list, we basically then annotate you, okay, this is structure hit top 1, and it also has a library hit. And that's how we do it. Yeah. Okay, then thank you a lot and have a good day.